Welcome to our discussion on evolutionary computation, a fascinating field that draws inspiration from nature's problem-solving abilities. These are powerful nature-inspired algorithms designed to tackle and solve complex computational problems effectively. Let's delve into genetic algorithms and explore their core components, which are fundamental to their operation. These components act as the essential building blocks for the entire evolutionary search process. First, we have the population, which is crucial for starting our search for solutions. A population is simply a collection of potential solutions, called individuals, to the problem we want to solve. Next, consider chromosomes, which are the blueprints for these potential solutions. These are encoded representations, like genetic code, for each of the possible solutions in our population. Within each chromosome, we find genes, which are specific parts of the blueprint. Genes are the individual components of a chromosome, representing distinct attributes or features of a solution. The fitness function is absolutely vital for determining how good a solution is. This function systematically evaluates the quality and suitability of each potential solution to our problem. Selection is the mechanism by which we choose the best individuals to move forward. It's the process of carefully choosing individuals from the current population that will reproduce and create offspring. Crossover is a genetic operation that allows for the mixing of information between solutions. This involves combining parts of two parent chromosomes to produce new, potentially better, offspring solutions. Finally, mutation introduces small, random changes into the genetic material. Mutation is crucial for introducing random changes to maintain diversity within the population and explore new solutions. Now, let's walk through the typical process flow of a genetic algorithm, step by step. The process begins with initialization, where we create the initial population of random solutions. After initialization, we move to evaluation, using the fitness function to assess each solution. Next is selection, where the fittest individuals are chosen to become parents for the next generation. Following selection, crossover combines genetic material from the selected parents to create new offspring. Then, mutation introduces random alterations into the offspring to ensure diversity and exploration. Finally, replacement updates the population with the new generation, continuing the evolutionary cycle. Let's explore evolutionary strategies, uncovering their defining principles and how they approach optimization. These strategies are particularly effective for optimizing continuous problems through adaptive mutations. A key principle is real-valued representation, which is how solutions are structured. In this approach, solutions are represented as continuous vectors, allowing for fine-grained adjustments. Evolutionary strategies are primarily mutation-centric, emphasizing random changes as a core mechanism. Mutation serves as the primary operator for both exploring the solution space and maintaining population diversity. Another important principle is self-adaptation, where the algorithm learns as it evolves. This means that strategy parameters, like the mutation step size, dynamically evolve over time. Evolutionary strategies are highly suited for continuous optimization problems. They are particularly effective for problems where variables can take any real value within a range. Today, we're diving into evolutionary strategies, a fascinating area of computational intelligence. Specifically, we'll explore two core selection models that define how these strategies operate. First, let's look at the mu plus lambda strategy, a fundamental approach in evolutionary algorithms. Here, mu parent solutions produce lambda offspring, expanding our pool of potential solutions. Then, the best mu individuals are chosen from both parents and offspring to form the next generation. Next, we'll examine the mu comma lambda strategy, another crucial selection model in evolutionary computation. Similar to before, mu parents still generate lambda offspring solutions in this model. However, here, only the best lambda offspring are chosen to advance to the next generation. Let's shift our focus now to swarm intelligence, a fascinating field inspired by nature. Swarm intelligence, or SI, explores collective, decentralized system behavior, where simple agents interact to solve optimization problems, inspired by natural swarms. Now, let's explore some key swarm intelligence algorithms and their natural inspirations. These algorithms draw directly from observing fascinating behaviors found in the natural world. First up is ant colony optimization, or a CO, mimicking how ants find food. It models ant foraging, where ants find optimal paths through collective decision-making. A CO uses simulated pheromone trails to effectively guide the search for the best solutions. You'll find a CO widely applied in routing, network optimization, and complex scheduling tasks. Next, we have particle swarm optimization, or PSO, inspired by bird flocks. PSO is inspired by the collective movement of bird flocks or schools of fish. Particles update their positions and velocities based on their own best and the global best solutions found. It's widely used for optimizing various functions and in training neural networks efficiently. Let's now visualize the complete evolutionary process cycle, understanding each step in detail. This cycle represents an iterative improvement process, evolving solutions over many generations. It begins with initializing a diverse population of potential solutions, our crucial starting point. Next, we evaluate the fitness of each individual to see how good it is. Then, we select the fittest individuals to become parents for the next generation. We apply genetic operators like crossover and mutation to create new offspring. These offspring then form the new generation, ready for further iterative improvement. Finally, we check for termination criteria to decide if the process should stop. All right, let's wrap up our discussion with a concise summary of all the important concepts we've covered today. Here are the key takeaways, the most important points you should remember from our exploration of evolutionary computation. First, remember that evolutionary computation, or EC, employs algorithms inspired by nature to solve complex optimization problems. Genetic algorithms, or GA, simulate natural selection through processes like population, selection, crossover, and mutation for solutions. Evolutionary strategies, ES, are great for continuous problems, focusing on real-valued solutions, mutation, and self-adaptation. Swarm intelligence, SI, algorithms like a CO and PSO utilize the collective, coordinated behavior of simple agents. EC methods are incredibly powerful, especially for tackling complex, multidimensional, and nonlinear optimization challenges effectively. Finally, remember that each evolutionary computation paradigm has unique strengths, making it suitable for different problem types.